morning. In the last lecture, I was talking about catalyst deactivation, and I told that the catalyst deactivation is the loss in the activity of catalyst with time. So, we defined the activity of a catalyst, and then this activity which is defined as the rate at any time t divided by initial rate, that is the rate at t is equal to 0, and rate can be calculated from conversion versus time data. So, one can have the conversion versus time data. So, if the catalyst deactivates, then the conversion will drop like this, or this can be calculated in terms of the selectivity of the product also, desired product, and rate. So, activity of a catalyst will drop with respect to time on stream, but I discussed last time, and that will depend on the order of deactivation also. So, experimentally one can find out the deactivation order also. So, in general one can write minus dA by dt, that is drop in activity as a function of time, some constant which may be your deactivation constant and will be a function of temperature, and times whatever the activity to the power n, where n is known as order of deactivation. Right. So, this can be find out the deactivation rate constant K d, K d is known as deactivation rate constant. And will be given by Arrhenius equation as a function of temperature. So, K d is a function of temperature, can be given K d at one temperature, say K d 1 or K d 0 e to the power minus E d divided by R t, where E d is the activation energy for deactivation reaction. So, one can use the differential method of analysis or integral method of analysis to find out the rate data with time on stream, and can then activity can be calculated as a function of time on stream, and then by using the differential method or integral method of analysis, what is generally done for determination of order of reaction and activation energy and rate constant, one can find out the deactivation kinetics or deactivation order of reaction and activation energy also. So, in general when you write the rate of a main reaction by knowing this function, that how activity drops for a given reaction as a function of time, then one can correlate this net rate or rate at any time t, which can be a function of activity which is a function of time times the rate which is a fresh catalyst rate, or minus R A disappearance of reactant for the fresh catalyst, that is initial rate. So, this A t is calculated from the deactivation kinetics, and then the rate at any time can be used for the design of the reactor. So, the rate expression in general can be defined by two ways. One is known as separable kinetics. So, where this deactivation function is independent of the geometry of the catalyst or property of the catalyst. In the second case, when the deactivation function is related to the property of a catalyst, then it should be a kind of non-separable kinetics. So, in this case most of the time we talk only a deactivation function separately and the kinetics of a main reaction separately, and then we analyze. Otherwise, in this case one needs to find out the surface property of the catalyst with time on stream, and then correlate it with the activity of the catalyst. So, as I said that ideally the activity should be 1, that is the catalyst should not deactivate. So, this is the ideal case, there should not be any deactivation in a good catalyst, but if you look at the practical catalyst, their activity decrease with time. So, conversion decrease, product selectivity decrease or yield decrease. So, productivity decrease with time on stream. So, this can be like a real catalyst, if this is drops like this can go like this also, or this is the severe deactivation of the catalyst, but is not desired. Actually, this you can see the activity becomes 0 after a certain period of time, and the drop is much faster right, a kind of exponential decay with very high order of deactivation. So, that is not recommended in a good catalyst. So, as I said now that the deactivation order or deactivation rate minus dA by dt is a firm function of activity of a catalyst, and this activity of a catalyst can be something like A, first order decay, if the deactivation is, this is known as first order decay. So, in the first order decay one can very easily write minus dA by dt is equal to k d times A, right. So, this is a kind of first order decay, and one can very easily integrate, because time t is equal to 0, the activity is 1, and t is equal to any time t, activity A is A. So, one can use the separation of variable and take the limit from 1 to A and time 0 to t k dt, and the integration can be done in this form, right. So, exponential decay of activity for the first order deactivation. If it is second order, then one can write. So, this is a first order decay. Second order minus dA by dt will be written as k d times A square, and then again the separation of variable. So, minus dA upon A square is equal to k dt, and then you integrate it from the limit 1 to A is equal to k dt, and then 0 to t. So, k dt, and one can again solve this equation. So, activity can be correlated as a function of time. So, whether it is first order decay or second order decay. So, one can very easily write the exponential relationships for the different kind of decay rates. Now, as I said that the deactivation mechanism may be different type. It can be because of fouling, that is the deposition of the coke. It can be because of the poison precursor. So, the rate drops because of the concentration of poison precursor, or it can be a kind of sintering where the surface area of the catalyst may be affected because of the recrystallization. So, the grain size increased, and because of that the surface area or active surface area of the catalyst decreased. This can be because of the blockage of the pore, because when the constant heating at high temperature, then the pores may they shrink, right. So, and depending upon that the pore size distribution change, and the surface area of the catalyst may be affected because of the sintering. So, this is what here the kinetics of deactivation for a poisoning type of reaction. So, here a poison precursor which is available in the feedstock itself and adsorbs on the surface of the catalyst. So, as I said that when poison precursor adsorbs on the surface, then the number of active sites available for catalytic reaction that decrease, and once this happens, then the activity of catalyst will drop permanently. So, and it will, because the poison precursor if it is present in the feed, then it will keep on adsorbing on the catalytic active site, and it will damage the catalyst. So, this is the main reaction where we are assuming that A adsorbs, which is a reactant species, it adsorbs on the active site of the catalyst S and gives a intermediate kind of complex which we have already discussed, A S, and this A S, this is your surface reaction. So, transforms into a species which is B S and some C, right, which is a product gas, and then B S gives you product B and the site is free. So, A gives you B plus C, this is the main reaction, but since the feed contains a poison precursor like sulfur, as I said, right, it can be sulfur compound, it can be nitrogen compound, or any feedstock may be oxygenated compound. So, that adsorbs on the surface of a catalyst and makes it P S, which is chemi-adsorbed poison precursor. So, this is the kinetics of the main reaction which we have already discussed earlier. So, minus R A, that will depend on your rate of adsorption of A, rate of surface reaction, and rate of desorption. So, any step may be rate controlling, and one can determine the rate of reaction, that is the rate of main reaction which is here K C A divided by 1 plus K C A plus K B K A C A plus K B C B. So, this rate of the main reaction can be different, but here we have written it in this form, assuming this step as a rate controlling. So, and adsorption and B, they are fast, A and B they are at equilibrium. So, the rate is fresh, this is the RA0 fresh catalyst rate, and this is the activity function when the catalyst is deactivating with time. So, activity is decreasing because there are the sites which are being blocked by the poison precursor. So, in this case if you look at the rate of deactivation R d is minus d A by d t, that is decrease in activity of the main reaction with respect to time because of the poison precursor adsorbed on the surface. So, this is written here in the form of K d dash times concentration of this poison precursor P to the power m times the activity to the power q. So, generally the poison precursor concentration and this whole term can be combined together because this is present in the feed itself. So, we can very easily write sometime here K d times A to the power q, where q is the order of deactivation and A is the activity and K d is the overall rate of deactivation, because C p is the concentration of the poison precursor present in the feed, which is taken as a constant here. But sometimes this may, that is the power to the by which the catalyst deactivator, suppose the sulfur precursor. So, the deactivation is much faster, and basically this kind of deactivation when you write, then your total site C t, if you calculate, that is nothing but the concentration of vacant site plus whatever the site adsorbed by A, you write it C A, site adsorbed by B and sites which are adsorbed by poison precursor. So, this is the term which is decreasing the activity of the catalyst. These are recovered because this A S gives you whatever the A plus S and B S gives you B plus S, but this C p is a kind of irreversible reaction, right. So, this C p remains in the denominator of the main reaction if you write the expression in terms of the adsorbed species concentration. So, that is generally not known. So, we write it in terms of some activity function, that is how much rate is lowered because of this poison precursor with time on stream. So, this is what the actually the rate is decreasing because the poison concentration is covering the active site of a catalyst. So, the available vacant sites are continuously decreasing with time on stream. So, this is C t 0 now in this case, but with time this C t is decreasing because this C p is continuously blocking the active site of the catalyst. So, this is written here if you look at C t 0 minus C p s basically, right. The same expression which we have written in terms of activity or how this rate is changed, because what we have written here in terms of deactivation, but same can be written in the form of this concentration of the poison precursor which is written here and the concentration of the vacant site C s, and that has been written here in terms of the concentration of poison precursor C p times C t 0 minus C p s, because C p s is permanently blocked or damaged site, right. So, C t 0 minus C p s is the concentration of the vacant site which is available and change with time on stream, because C p s is increasing with time. So, this concentration total sites which are available, that will decrease. So, R p s can be written in the form of K times C t 0 minus C p s times C p. So, this is the rate of formation of poison precursor which is written here. Assume the rate of removal of gas stream onto the catalyst site is proportional to the number of sites that are unpoisoned and the concentration of the poison precursor in the gas. Just like we define the rate is proportional to the concentration of the poison precursor or partial pressure of the poison precursor multiplied by the concentration of the vacant site where the poison can adsorb or on the surface of a catalyst. So, this RPS can be written in terms of dCPS by dt, that is how your catalyst is deactivating with time will depend how the poison is adsorbing on the surface of a catalyst. So, rate of adsorption of poison precursor on the surface of a catalyst is equal to some constant which is K d, which is here K d times C t 0 minus C p s times C p, right. This is based on the surface reaction which we are assuming in terms of the mechanism here for the poisoning. and one can directly correlate it in this form also by just doing the experiment and calculate the rate with time on stream and then calculate the order of deactivation and rate constant, decay rate constant. So, this kind of mechanism, that is the poison precursor mainly in the petroleum refinery, if you look at the sulfur precursor, nitrogen in the feed or oxygen compounds in the feed like phenolic compounds, they adsorb on the surface of the catalyst, and the mechanism of this catalyst need to understand in order to develop or design a novel catalyst system for a given process, right. Hydro treatment just as an example I am talking here. So, stability profiles generally if you look at the high rate of deactivation is mainly due to the coke deposition in the case, because initially your concentration if you look at here, even for coke deposition or poison, initially this concentration or vacant site concentration is very high. So, the rate of poisoning will be high and finally, it will reach to kind of asymptotic poisoning rate. So, finally, the rate will decrease as the concentration of the poison site decrease, vacant site decrease. So, coke deposition finally reach to the equilibrium, but metal deposition, if the metal is there, they are adsorbing on the surface of the catalyst irrespective to the fraction of the vacant site. So, that increase. So, if you look at this graph in the case of hydro treatment reaction, which I was just talking for example of hydro treatment. So, the activity of catalyst drops like this. So, this is the activity profile. So, catalyst activity which is calculated with respect to the conversion with time on stream. So, that decrease with time. If you look at the coke, so coke deposits on the vacant sites, right, active site of a catalyst. So, this is a kind of asymptotic coking rate. So, initially it increase something like it may be Cc, the coke formation, it can be related to A times T to the power n, that T is the time and in minute and A is a constant, n is the order of deactivation and Cc may be the concentration of carbon deposited on the catalyst, which can be defined in terms of gram per unit area of the catalyst, right, or gram per gram of the catalyst. So, either units can be used. So, this is just a coke formation rate, which can be written in terms of the concentration of the coke precursor also, right. So, that can be related either in terms of T. So, generally this is where here n is roughly 0.5, that is a kind of order of deactivation in terms of this equation. So, n is roughly 0.5 here, right. So, this is the kind of asymptotic coking rate, but metal formation increase continuously, that is the hydro demetallization is to be done in order to remove the metal from the catalyst. So, so metals concentration increase continuously, but this coke formation is a kind of asymptotic coking rate and activity of the catalyst drops because of the combined effect, right. So, that is what the content of poisoning which has been shown here in this graph. So, fouling, that is first thing is the poisoning and second is the fouling. Fouling as I said is a carbon or dirt. So, deposition of the carbonaceous material on the surface of a catalyst, that is known as fouling, right. So, it can be physical, right, physical deposition or mechanical deposition of species from the fluid phase. So, sometime the feedstock may contain the coke precursor, just like as I said aromatics, right. If the feed contains more amount of aromatic, then the carbon on the catalyst will be more. So, that is because of feedstock. Sometime it may be because of the carbon or the catalytic activity, that is the acidic catalyst. So, acidic catalysts have more tendency to form coke, right. The coke formation on the acidic catalyst will be more. So, that is if the feedstock itself is a more prone to coke formation, then the catalyst acidity should be reduced accordingly. So, one needs to identify, say like the zeolite catalyst, silica alumina catalyst, they are highly acidic in nature. So, coke on those kind of catalysts will be higher if the feedstock itself is a prone to coke formation, right. Aromatic feedstock, as I said atmospheric gas oil, vacuum gas oil. So, they are prone to coke formation because they contain the larger molecular weight of condensed polyaromatic, because coke is nothing but a condensed polyaromatic hydrocarbon. So, I will talk on that little later. So, this is nothing but again when the coke or carbon deposits on the surface of the catalyst, that will either block the active site of the catalyst, right, or block the pore of a catalyst. So, basically diffusion phenomena will change when the pore size of the catalyst is decreased, right. So, you will have more diffusion resistance in the pore of a catalyst, because the transport limitation, if you look at, again it is mass transfer, then diffusion and chemical reaction. So, mass diffusion limitation, if you look at, the pores are blocked. So, your diffusion resistance will be more. So, it may be it may happen that because of coke formation, the diffusion may be a rate controlling step in that case, right. So, one needs to check all these things when you look at the deactivation of the catalyst. So, this is very common when you look at any hydrocarbon reaction, because these hydrocarbons are prone to coke formation. So, carbonaceous material being deposited on the surface of the catalyst, right, and they decrease the activity of the catalyst, and that is known as fouling. So, as I said earlier also, the amount of coke deposition can be reported, right. So, basically the determination of coke can be determined, because coke is a kind of a material which can be burned off. So, one can remove the coke from the catalyst just by burning, and that is known as regeneration of the catalyst. So, this basically when you burn in terms of controlled oxygen, so this gives you CO, CO2, right, and you have water also, CXHY. So, some water also. So, you get this, because coke may contain your hydrogen or CXHY. So, ultimately you may get all these things, right. So, one needs to control the CO to CO2 ratio in the flue gas. Especially when we talk a regeneration of the catalyst. Because this process is exothermic. So, it is an exothermic process. So, heat generates. So, one needs to control, because if the catalyst is being burned in presence of oxygen at around say 550 degree centigrade, this is the generally the temperature required for regeneration, and if temperature exceeds say 700 or 800, then your catalyst may damage. So, zeolite say they have they cannot sustain the temperature more than 550 or 600, say Jdesm 5, right. So, they are not stable with respect to high temperature. So, one needs to control this in order to control the stability of a catalyst, or otherwise the crystals will grow in size or the catalyst will get sintered. So, one needs to look at that regeneration. So, what I mean to say that regeneration of a catalyst is possible, but for that one needs to find out how coke forms. So, amount of carbon formed as a function of time, right. So, this will be a function of temperature also, because higher the temperature, more will be the severity of reaction. So, generally it will known as asymptotic coking rate, right. So, this will be a kind of profile which is related as a function of temperature, right, and one can very easily calculate it at different temperature. So, increasing the temperature, the coke on the catalyst will increase, and this is known as asymptotic coke rate formation. So, this can be related some function t to the power n, which is given here in this form of expression, right. So, these are a kind of empirical expression which can be determined experimentally by doing the experiment with different catalyst and different feedstock, and one can use this expression. So, in the case of fouling, as I said, the deposition of carbonaceous material on the surface, right, and this is related to as a function of amount of carbon deposited on the catalyst, right. So, that is the catalyst surface CC. So, that is the coke deposited, which I told you that it can be reported gram per meter square of catalyst, right. It can also be reported gram per gram of catalyst also. So, A and N are known as fouling parameter and depend on the type of gas being processed. So, once this is known, then the rate of coke formation dC by dt can be calculated, right, or that can be correlated in terms of the activity, how the activity is related with the coke formation, because once more coke is forming, then activity will drop. So, A will have some function of coke, and this will decrease. So, activity will decrease when the coke is forming on the catalyst, right, because active sites are blocked, and there can be different correlations like this, right. So, this is one correlation, empirical correlation, where it is shown that the activity drops 1 over 1 plus the amount of carbon per gram of catalyst to the power p. It can be written in terms of time also, which is written here. So, it can be given like this also, right. It can be exponential drop also. So, activity is written e to the power minus alpha c c, right, where again c c is the gram of carbon per gram of catalyst. It can be written in this form also 1 over 1 plus alpha 2 times c c. So, these all are empirical constants which can be determined experimentally. So, one needs to do experiments like this at different condition of temperature, right, and measure the carbon deposited on the catalyst with respect to time. So, carbon deposited on the catalyst can be determined by TGA operators, right. So, one can determine the carbon and then can correlate the expressions like this and report the activity in terms of the concentration of carbon deposited on the catalyst. So, activity will drop continuously like this. So, this activity function can be added with the main reaction rate and then design can be done, right. So, the coke deposited, as I said, can be measured by thermogravimetric analysis, which we have discussed, that we heat the sample, the known amount of mass of the catalyst you take in a pan and then heat it with different temperature rates, right, at different temperature rates and up to a temperature say 1000 degree centigrade, because the nature of coke may depend on the temperature. It may be a graphite type carbon, it may be amorphous type, it may be kind of carbon nanotubes, nanofiber. So, needle type of coke, that is a production process by atmospheric gas oil or vacuum gas oil, right, the delayed coking unit, Wisbreaker unit. So, these are the units where the coke is being produced, right, in order to make them commercially viable for some other process, right. So, that can be done. So, one can measure the amount of carbon deposited as a function of time and at different temperature. So, how much coke is removed when you burn it in TGA, one can find out and then you can correlate it again, or you can understand the mechanism of coke formation also. So, this falling of coking mechanism itself is a complex phenomenon. So, when you look at a commercial process where you do the refinery operation of cracking, hydrodesulfurization, right, the coke formation is to be removed, right, or minimized. So, you need to identify the optimum catalyst composition, because I told that when the coke deposits, the activity of catalyst drops, right. So, one can add some promoters, right, in order to reduce the coke formation. So, just like in cracking, a small concentration of potassium can be added, right, because the presence of potassium inhibits the coke formation, because these acts as a gasifier agents, right. Same thing, the ceria is added, zirconia is added, because they have the excess oxygen in the lattice structure. So, all these kind of materials like potassium, right, ceria as a support, basic support, kind of basic support, zirconia can be added as a promoter, right. So, these the basic promoter, kind of basic promoter. So, basically the, as I said, that more acidic is the catalyst, your deactivation will be higher, right, because carbon formation will be more on acidic catalyst. So, it means the one thing is that acidity to be controlled. I am not saying acidity is to be reduced, controlled, because the main reaction rate will also decrease when you decrease the acidity, right, especially when you have a cracking type of reaction. So, one needs to find out that. So, means optimize the condition. So, temperature is one thing, because high temperature favors the coke formation. If you have a higher temperature, then more coke will form during the reaction, right. Pressure again has some effect, right. So, you need to find out high pressure or low pressure. So, generally high pressure will avoid the coke formation, right, but higher hydrocarbon partial pressure will increase the coke formation, right. The concentration of coke precursor will increase the coke formation. So, equilibrium must be in between rate of coke production and rate of coke removal. So, reactor cum regeneration. So, generally if you look at your FCC cracking, just as an example, fluid catalytic cracking. So, in this case, in the fluid catalytic cracking, the coke formation is severe. So, generally silica alumina type of catalysts are used, or zeolite type catalysts are used, ZSM 5 type catalyst, and feedstock is your atmospheric gas oil or vacuum gas oil. So, these are the feedstock. So, all these feedstock contains your higher molecular weight compounds and also aromatics, right. So, these tend to form coke. So, large amount of coke will form when you do the cracking of these kind of feedstock with this catalyst. So, generally the residence time should be as low as possible. So, 1 to 5 second is the residence time which is kept in the reactor during the cracking, right. So, the system if you look at, in that case you need a system where you have continuously feed the catalyst like this. So, feeding of the catalyst is done along with the feed, right. So, you have the feed, say vapors of the AGO along with some say steam, right, and you have some say that can be used and some fluidizing media or either steam or feed vapors itself. So, these are the vapor and the catalyst is here inside the reactor, fluidized bed condition, right, and this can be a riser type of cracking, because most of the cracking takes place in the initial portion. And then you have a hopper here, cyclone separator, and the catalyst is the vapors hydrocarbon will go into this section and the catalyst is taken into the another unit which is known as spent catalyst, that is after reaction, right. So, deactivated catalyst and that will be taken into the another unit like this. So, your catalyst comes like this continuously, right, and where you pass the oxygen from the bottom and then your catalyst is regenerated and you get the flue gas. So, that is CO, CO2, right, and water whatever like this, and so and oxygen or nitrogen whatever if you are using the air, and then the regenerated catalyst is taken back into the reactor system. So, like this. So, this is your regenerated catalyst. So, this is one kind of simple design that how reactor and regenerator they are placed in parallel, right. So, you have a reactor here which is a cracker, right, and this side it is a regenerator and continuously the catalyst is recycled back and regenerated and the cycle continues, right. So, now this design of this kind of system will depend type of licenser, or different kind of designs are available for utilizing these kind of feedstock. So, you need to control the temperature here, this there the temperature may be around say 550 degree centigrade, right. So, the catalyst comes at 550 and when you have the heating here, then temperature can go up to 750 degree centigrade, because it is exothermic reaction. Here it is endothermic reaction, right. So, endothermic reaction here, exothermic catalyst regeneration reaction here. So, you need to control the oxygen ratio in the flue gas, right, or CO to CO2 ratio here, right. So, how much oxygen is to be given to burn a given type of catalyst amount. So, CCR which is the catalyst circulation rate, right, and that will decide your reactor inventory, size of the reactor, right here. So, this is a very complex system. If you look at a design of reactor and regenerator with proper heat balance, right, mass balance and include the kinetics here, right. So, kinetics of main reaction, kinetics of deactivation reaction and then control CO2 CO2 ratio in the flue gas, so that there should not be any after burning, right. The catalyst temperature should not exceed more than 750 or 650 degree, that depends on the type and the stability of the catalyst. So, catalyst stability also need to be enhanced. So, this is what you need to look when the carbon deposits on the catalyst or catalyst deactivates. So, reactor regenerator combination or a novel kind of reactor system design is required. So, this is what I mean to say here, that you need to look at that how much carbon is depositing on the catalyst per gram of catalyst, right, per hour per unit time, and how much carbon is being removed from the catalyst. So, you need to look at a controlled carbon, say if you are making a benchmark, then coke in regenerated catalyst should be less than 0.1% and starting material may have around say 5%. So, from 5 to 0.1% how the carbon has to be removed from the catalyst, right, and that needs to be calculated and accordingly this sizing is to be done or kinetics is to be discussed, right. So, the coke formation can be reduced by running the reactor at higher pressure, right, and you can add the hydrogen by, that is the partial pressure of hydrocarbon can be reduced, less like in a reforming process this is done, that operation is done at high pressure and to reduce the coke on a catalyst, because coke formation is a function of temperature, is a function of partial pressure, is a function of concentration of the poison precursor. So, catalyst deactivated by coking can usually be regenerated by burning of the carbon. That is what I discussed, that carbon reacts with oxygen and gives you carbon dioxide. So, the fouling phenomena, that is the deactivation phenomena by coke formation or fouling, is defined basically the deposition of carbonaceous material on the surface of the catalyst, and how much carbon is deposited, that is what we have discussed. And this activity level is a function of the amount of carbon deposited on the surface of a catalyst, and that is what the expressions, different kind of expression that can be used for this purpose. So, different kind of rate expressions have been used here. So, activity is expressed as a function of coke formation, and that is given by e to the power minus alpha times coke formation. So, that is what I discussed earlier, and C c to a to the a t to the power n. So, one can use it either expression, or one can design the kinetics of coke formation or find out the expression for coke formation. So, sometimes as I said, the same coke formation which is C c I have written as a function of the time on stream, that is T is the time on stream, T to the power n, or the concentration of the precursor which is tending to form coke to the power n, which can be written sometimes as a function of feedstock concentration itself, right. So, one can very easily do that and can find out. So, here if you look at just an isomerization reaction, which is a reversible isomerization reaction, and C is the precursor which tend to form coke. So, this is present in the feed itself, a coke precursor. So, and A is your main reactant, right. So, strongly adsorbs on the surface and not found in the gas phase. So, this C is the coke precursor. So, A plus S gives you AS, that is your main reaction, right. R A for this. So, we have already discussed this. So, very quickly I will go through that. So, rate of adsorption of A, which is a reactant species, and here we are writing that KSR, surface reaction rate constant for this, minus the concentration CAS, that is already been done. So, I am quickly writing minus CBS divided by KSR. So, generally this is the surface reaction rate constant, which is controlled based on this type of expression here, right. So, that is rate controlling, where AS gives you a BS, a product species. So, rate will be proportional to K1 times the concentration of this precursor minus K2 times the concentration of this precursor, and K1 and K2 has been taken out. So, that will become a rate constant KSR, that is a surface reaction as the rate controlling step. So, you will have CAS, that is the concentration of the adsorbed species, which is like this, minus the concentration of adsorbed species B divided by the equilibrium constant for the surface reaction rate constant. So, this part we have already discussed when we were discussing the Langmuir type of mechanism. So, one can very easily look at that. So, one can write these expressions CAS, CBS in terms of the total concentration of the known species. So, site balance, as I told you. So, total concentration of the site will be CAS plus CBS, right, and part of that activity is decreased because of the concentration is decreasing, because the poison is depositing, right. So, we introduced a factor here A to incorporate that. So, one can write that in the denominator of the adsorbed species, or one can write it in terms of the activity function, right. So, this is same expression KSR times the, you have just calculated CAS and CBS in terms of the known concentration, like this for CAS, right. So, at equilibrium, rate of forward reaction is equal to rate of backward reaction. So, one can very easily find out CAS, right. So, that is substituted here in terms of the equilibrium constant which has been taken out, and same thing for CBS. So, CBS also, because CBS will BS desorbs and gives you B plus S. So, one can very easily write down the expression, right, and overall equilibrium constant can be calculated from this reaction, A goes to B, right. So, this is your overall equilibrium constant. So, basically this is your rate when the catalyst is fresh. So, one can write it like this R A at t is equal to 0, right, and that is determined from the Langmuir type of mechanism, simple, right. So, and I multiplied this with the activity of a catalyst, and activity determination function is separate. So, one can write this activity which is written here in terms of the concentration of vacant site plus concentration of sites covered by A plus concentration of sites covered by B plus the concentration of the sites covered by Poisson precursor. So, this is the number which will come in the denominator of Langmuir-Hinshelwood expression, right. That is, when you write this minus R A is something like K times P A divided by 1 plus K A P A, because it is adsorbing, right, plus K B P B, because this is also adsorbing, right, plus additional term which we got now because Poisson is here. So, K times some Poisson precursor times the concentration of the Poisson or the partial pressure of that Poisson precursor P P. So, this is the unwanted term which has arisen in the denominator. This is the term which is because of the chemical reaction, you cannot eliminate that these terms, right, because they are strongly chemisorbed, but they transform into the product due to the course of time, right, because of the surface migration or surface reaction. But this Poisson precursor is not taking part in this, and this is a kind of irreversible chemisorption of the Poisson precursor, or something like C plus S is converting to C S. So, C plus S gives you C C S, and this term is arising because of this, an irreversible Poisson precursor. So, that has also taken part in terms of total site balance, right. So, that will come in the denominator. So, rather write, either you write it in the denominator and determine the concentration of this, because this is not very easy to determine, right, the concentration of CCS, right. So, you can write it in terms of the concentration of the feedstock, right. So, partial pressure of the feedstock and some fraction of that, or one can write the activity term and then calculate rate because of these concentration of the Poisson precursor and how much is decreased. So, minus dA by dt can be calculated and then activity function can be substituted. So, this details have been given here further. A s gives you B s, and finally, B s comes to B plus s, which we already done, and C t is C s plus C s plus C B s plus C C s. So, Poisson precursor, and this C C s comes from this C plus s gives you P s, right, or C s. So, one can very easily write a site balance in terms of C t. So, C s, C B s and C C s can be determined from the constant, equilibrium constant. So, this is what written here C t. So, C s is the total concentration, right, times 1 plus. So, C s is the vacant site concentration. So, C v or C s plus 1 plus K A C A, that is the adsorbed species of A, K B C B adsorbed species of B, and time plus additional term which is C C over C s. So, this is not known basically, right. You cannot find this experimentally also, very difficult, right. But overall activity or drop in conversion can be estimated, which is because of this term, right. So, that is what is shown here, that one can find out these concentrations and then look at the deactivation because of surface coverage, this number, right. So, your rate of reaction which I wrote there, right, can be written instead of activity term, which is I have here shown that one can write this term instead of writing the terms of the denominator, right, and related to the activity of a catalyst. So, here now this is the term which has come in the denominator because this is there, right. If there is no deactivation, then this term is 0, right, then A is 1 all the time, right. So, you have 1 plus K C A plus 1 plus K B C B, your usual Langmuir-Hinshelwood type mechanism, right, for surface reaction rate control, and species A is adsorbing, species B is adsorbing on the surface. So, one can very easily write down the expression. So, the meaning here is that for the reversible isomerization reaction, where C is the precursor, coke precursor for the formation of carbon, and species are strongly adsorbed on the surface, right, this is adsorbed and not found in the gas phase. So, A plus S gives you A s and your rate of reaction, which can be written in terms of R A 0 times A, or you can write in terms of surface reaction rate constant, adsorption equilibrium, site concentration which is at T is equal to 0 times whatever the driving force, right, concentration driving force. So, C A minus C B by K, because overall reaction is this, right. So, this is overall equilibrium constant for reaction, which we already discussed, and divided by the terms which adsorbs on the surface. So, 1 plus K A C A plus K B C B, and this is what the C C S divided by C S, right. So, neither term is measurable, right, thus some empirical correlation is necessary. So, these two are unknown, but you know that your rate is decreasing. So, because of this, right. So, with time on stream how much is dropped. So, one can correlate this, and that is what the activity of a catalyst as a function of time on stream. So, basically this is the mechanism, actual mechanism, that the rate is decreasing because of the poison precursors are covered, or poison precursors are covering the active sites of the catalyst, right. So, deactivation by site coverage, which I have shown, because the coke formation mechanism is very difficult to understand, right. So, this is not well known, right. So, we write the in the form of empirical correlation. So, as I said, minus dA by dt. So, that is my phi deactivation function, right. So, some commonly employed expression if you look at. So, this is what has been defined, a kind of deactivation function which is related to coke formation, right. So, this phi is related to A t to the power n, something like that, related to carbon formation, right. So, K 0 K A times phi C A minus C B divided by K, what you have seen before, divided by 1 plus K A C A plus K B C B. So, now we have removed that term from the expression. So, from this expression we have removed this third term, which was C C S divided by C S, because this is not known, or experimentally also one cannot determine them. So, but one can write down the expression in the form of some deactivation function, and that is what done here in this case. If you just look at the hydrogenation or dehydrogenation catalyst, which is just the mechanism of coke formation shown here, right. A surface, right, a dehydrogenation catalyst, and you have a precursor, right, a feedstock, right. It can be the dehydrogenation in terms of the, when you look at the formation of the aromatic hydrocarbons, right, and they tend to form coke, right. So, basically the dehydrogenation reaction is nothing but removal of hydrogen from the feed, right. So, it can be something like ethane dehydrogenation and you get ethylene, right, which is a kind of cracking basically, right. So, so for this case dehydrogenation catalyst, where metals or oxides are used as a catalyst, right, the coke is formed on in a different mechanism. So, mechanism of coke formation is very complex, and this varies on the type of metal and the type of feedstock. So, the coke is formed in a different matter compared to the acid cleavage of hydrocarbon. Generally, it is assumed that during cracking reaction the hydrocarbon adsorbs on the surface and then it dehydrogenates basically, right. So, basically it is a cleavage of carbon carbon bond, right, not the so, it is a kind of scission, beta scission, that is the bond breaks into points, and from how does this bond breaks, that will depend on the type of metal and also the bond energy. So, bond theory is to be understood in terms of carbon hydrogen, carbon carbon, double bond and triple bond, and the surface substrate which has the kind of protons available, acidity of the catalyst, right. So, that is one thing here if you look at in that form, right, the cleavage of a hydrocarbon, a large molecular weight, so something like a normal heptane, right, and that is being cracked, right. So, heptyl radical forms, right, or methyl radical forms, hexyl radical forms, and so on change progresses, right. So, that is a different kind of mechanism, but in dehydrogenation the hydrogen is being removed from the catalyst, right. So, in that case hydrogenolysis also happens, right, and that lead to formation of the carbon molecule, that is coke formation. So, these are highly reactive, whatever the dehydrogenation, if you look at the product, or hydrogenolysis, right, the formation of carbon fragments which are the CX type. So, they are highly reactive and are bound in a carbide like fashion or present in a pseudo graphite form. So, the carbon may be a different form of carbon, right, a graphitic form of carbon, right. So, in the presence of acid support material, the carbon fragment migrate from the dehydrogenation center of the metal to the support. So, this is a kind of migration from the metal to the support side, where they are cleaved analogously to acid catalyst. So, this is what the mechanism shown here, that this is a kind of support. So, this is a dehydrogenation active site. So, the species comes here, right, and adsorbs on the surface, and that it cleaves like this. So, a kind of coke formation mechanism you can see here. So, hydrogen is being removed, right, and then this species has migrated with the support, which has acidic sites on the support, right. So, more coke formation on this kind of acidic supports. So, you need to control that, right, or add some kind of promoter to reduce this. And finally, if you look at here, that makes a dehydroaromatization type reaction, right. So, further hydrogen is removed and it starts to form a ring compound, cyclic compounds, right. So, then more and more hydrogen is removed and finally, it gets a polycyclic aromatic hydrocarbon, right. So, that is your coke carbon precursor. So, finally, this will result in a coke formation. It is completely nothing but a polycyclic aromatic hydrocarbon, condensed polyaromatic hydrocarbon. So, here the dehydrogenated coking that mainly occurs in the catalytic reforming. So, reforming catalysts are very much prone to coke formation, right, large amount of coke forms. So, the catalyst life drops faster. Same thing for the hydrodesulfurization also, because feedstock itself contains a lot of coke precursor, right, and in cases of metal contamination of the starting material, because as I said, the metal continuously deposits on the surface of the catalyst, that is again a fouling, right. In the catalytic reforming process, generally to avoid coke formation, the bimetallic catalysts are preferred, right. So, if you have a bimetallic catalyst, so these type of catalysts have shown the reduction in the coke formation. So, the catalyst life has been improved by using the platinum rhenium type of catalyst, which is a bimetallic catalyst, right. The details mechanism I am not discussing at this point, but one can very easily use this kind of bimetallic catalyst, that is rhenium to platinum, and it greatly increase the stability of the catalyst, which is shown here, right. So, you can see here that platinum rhenium on alumina catalyst, right, the activity is almost constant, right, and the catalyst can last years, right. So, this can have 3-year life, right, 1.5, 2 year, 3-year life. But if you look at here, in this case the catalyst life is just a week, which is a platinum alumina type, right. So, platinum alumina catalyst has a kind of life which is of weak order, but if you do the operation at high pressure, the life can be enhanced to months. So, it means you have two options. One thing, you optimize the process condition, right. So, it needs optimization. So, in order to reduce the coke from the catalyst, you do not operate the reaction at very high temperature, right. High temperature will not be good, but high pressure may be effective. So, one needs to do the reaction at higher pressures, right, and simultaneously one needs to look at a novel catalyst system, just like a bimetallic catalytic system, where the activity of a catalyst is, or stability of the catalyst is enhanced because of the presence of rhenium in the catalyst, right. So, this is a kind of reforming catalyst which is used for the reforming of naphtha, right. So, reforming of naphtha generally is done to produce more and more aromatic hydrocarbon, right. So, and idea is that reformated gasoline, when the desired to high octane gasoline. So, reformated gasoline is produced by the reforming of this naphtha compound, right. But nowadays you know that the high aromatics may not be desired. So, this can be used for the blending purpose, right, and to produce the aromatics which can be used for the petrochemical industry or specialty chemicals. So, once you have a kind of deactivation, you need to design a complete reactor, right. So, you need to find out the kinetics of the main reaction, you need to find out the kinetics of a deactivation reaction, right, and then correlate these two together, right, main reaction, deactivation reaction, and then combine and use it for the reactor design. So, as I said that fluid catalytic cracking is one, but moving bed reactor, straight through transport reactor, these are other kind of reactors where continuously the feed is being passed. You find out the what is the residence time required in a reactor, and then take the catalyst into the other regenerator reactor unit and regenerate and send it back. So, in all cases you need to write a mole balance equation. So, which is already you have done or we have discussed this F A naught dx by dz is equal to minus R A dash, right, or in terms of mole volume. So, R A times area of cross section whatever R A triple dash times A C. So, this is your area of cross section of the reactor, right. So, one can very easily write the rate of reaction in terms of moles or per unit volume of the reactor or per unit mass of the catalyst, right, and can write the expression. So, F A naught dx by dz is simply mole balance equation, right, which is simply your minus R A times the area of cross section. Stoichiometry can be different depending on the type of reaction. So, A gives you B plus C. So, C is a kind of coke precursor, right, a coke which deposits on the surface of the catalyst. The concentration of A and B can be defined based on this C A is equal to C A naught 1 minus X A, which already has been discussed. Same thing C B, because 1 mole of A reacts 1 mole of B will form. So, F A naught X or can be written in terms of the concentration. So, C A naught times X, right. If it is a gas phase reaction, so all of you know the homogeneous reaction kinetics. So, that has been used here. So, the change in volume, because this is a solid coke which is deposited on the catalyst and this is your B which is a gas phase. So, there is no change in the volume of reaction, right. So, fractional change in volume is 0. So, your epsilon is 0, right. So, this is the no change in volume of the reaction, right. Temperature T is T 0, P is P 0, volume flow rate V is V 0 and superficial gas velocity which is defined as the volumetric flow rate divided by the area of cross section, right. So, that is generally basically very important factor when you look at a straight through transport reactor or a moving bed reactor. So, how much time a catalytic species or catalyst spends inside the reactor, that will depend on this superficial gas velocity, right. So, T time required in a reactor will depend on the length of the reactor divided by the velocity of the gas, right. So, that is height of the reactor basically, or one can design the height of the reactor or size a reactor if these two things are fixed and the conversion is fixed, right. So, we will talk on that. So, I stop here and I will continue it next time.